The most terrifying things in the universe are not the monsters that scream. They are the ghosts that wait. For decades, we have been hunting black holes by looking for violence. We look for the eaters, the cosmic beasts that rip stars apart and shine like beacons across the galaxy. We assumed that if a black hole was close to Earth, we would see it coming. We assumed we would hear the roar, but we were wrong. The loud ones, the monsters, they are rare, but the silent ones, the sleeping giants that have finished their meals and are now just drifting in the dark, they are everywhere. New data has revealed a horrifying truth. Our solar system is not floating in empty space. We are walking through a minefield. Right now, hiding in the glare of familiar stars, are dormant black holes. They don't have accretion disks. They don't emit X-rays. They are invisible to our telescopes until we get too close. Just 1/1500 light-years away, in our cosmic backyard, lies a monster that we never knew existed. It isn't eating. It isn't shining. It is just watching, and it is not alone. Tonight, we are not looking at distant galaxies. We are leaving the safety of the sun to take a tour of our nearest neighbors, from the sleeping ghosts of Ophiuchus to the invisible stalkers in Centaurus. Welcome to the dark side of the Milky Way. This is the graveyard next door, and the gates are open. The night sky is the greatest illusion in human history. When we look up, we convince ourselves that we are seeing the universe as it truly is, a vast tapestry of light scattered across an infinite dark canvas. We name the constellations, chart the planets, and navigate by the steady glow of the stars. We have convinced ourselves that the cosmos is defined by what shines, that existence is synonymous with visibility. But this is a lie born of our biological limitations. Our eyes are evolved to detect photons, so we have ignored the shadows. We assumed that if something was massive, it would blaze with fire. We assumed that if a monster lived nearby, we would see its teeth. We were wrong. The universe is not mostly light. It is mostly gravity. To understand the true nature of our cosmic neighborhood, you must look past the bright veil of the Milky Way and focus on a seemingly insignificant patch of sky in the constellation Ophiuchus, the Serpent Bearer. For generations, astronomers swept their telescopes across this region and recorded nothing out of the ordinary. They catalogued the stars, measured their brightness, and moved on, assuming the map was complete. There was a star there, a yellow G-type sun, remarkably similar to our own, sitting roughly 1,500 light-years away. It appeared to be living a solitary life, drifting through the galactic arm in peace. It was just another number in a catalogue of billions, a speck of dust in the grand cathedral of the galaxy. But in the year 2022, a space observatory known as Gaia changed everything. Gaia was not looking for pretty pictures. It was looking for movement, mapping the precise position of over 1 billion stars with an accuracy equivalent to spotting a coin on the moon from Earth. The data Gaia returned was unsettling. The telescope had been tracking that ordinary sun-like star in Ophiuchus, and the numbers didn't add up. In a universe governed by Newton and Einstein, objects in motion tend to stay in straight lines unless acted upon by a force. But this star was not moving in a straight line. It was wobbling. It was tracing a distinct, rhythmic ellipse through space, whipping around a central point at high velocity. The mathematics of orbits are absolute. There is no wiggle room, no ambiguity. For a star to move like that, it must be orbiting something else. It must be locked in a gravitational embrace, with a partner massive enough to swing it around like a toy on a string. Astronomers calculated the mass required to generate such a pull, and the result was undeniable. The invisible partner had to be roughly 10 times the mass of our Sun. A star of that size should be the brightest object in the sector, a blazing blue giant visible for thousands of light years. But when they looked at the center of the orbit, they saw nothing. This is the terrifying beauty of Gaia BH1. It is the closest black hole to Earth ever discovered, and yet it is entirely invisible. In the past, every black hole we found gave itself away through violence. We found them because they were messy eaters, stripping gas from neighbor stars, heating that material to millions of degrees, and screaming out in X-rays that we could detect across the galaxy. We associated black holes with destruction, with glowing accretion disks and relativistic jets that pierce the void. But Gaia BH1 challenges that entire narrative. It is dormant. It is not feeding. It sits in the darkness, 10 times heavier than the Sun, completely silent. It has no glowing ring of fire to mark its event horizon. It has no jet. It is simply a tear in the fabric of reality that refuses to interact with the light around it, save for the subtle tug it exerts on its companion. The discovery of Gaia BH1 forces us to confront a statistical probability that is far more haunting than any quasar. We only found this black hole because of extreme technological precision, because we just happened to catch a companion star wobbling at the right angle. A dormant black hole is the perfect stealth predator. No radiation, no light, no interaction. We only see Gaia BH1 because it has a partner acting as a witness. But most massive stars live and die alone. If a solitary star collapses and goes dormant, it becomes completely undetectable to our current instruments. It becomes a gravitational landmine, floating in the dark. It forces us to ask, how many others have we simply walked past without knowing? Consider the distance. 1,500 light-years might sound like an eternity to a species that has barely reached its own moon, but in galactic terms, it is our front porch. The Milky Way is 100,000 light-years across. For a black hole to be found this close suggests that they are not rare anomalies relegated to the deep core of the galaxy or distant clusters. It suggests they are everywhere. If you were to take a random sample of the ocean and find a shark in the first cup of water you scooped up, you would have to assume the ocean is full of sharks. Finding Gaia BH1 so close to Earth implies that the Milky Way is teeming with these silent graves. There could be hundreds of millions of them drifting between the stars. There is also a profound mystery in how Gaia BH1 came to be. Standard stellar evolution tells us that to create a black hole of 10 solar masses, the progenitor star must have been a massive giant, probably 20 times the mass of the Sun. When such a star dies, it usually detonates in a supernova, an explosion so violent it outshines the entire galaxy. If the Sun-like star we see today was orbiting that giant when it exploded, it should have been destroyed. The blast wave should have stripped its atmosphere, or the sudden loss of mass should have flung it out into the void. Yet, here it is. The Sun-like star is intact, orbiting happily, as if the cataclysm never happened. This implies that our understanding of how black holes form is incomplete. Perhaps this black hole didn't explode at all. Perhaps it simply collapsed, swallowing its own fire in a direct implosion, vanishing without a sound. This silent neighbor serves as a tombstone for a star that once lived fast and died young, but it is also a mirror. We look at the sun-like star orbiting it, a star very much like our own, and we see a dark reflection of our own solar system's vulnerability. That star is living on the edge of an abyss, yet it continues to shine, likely unaware of the monster it dances with. It reminds us that stability is a local phenomenon. We feel safe because our sun is solitary. But Gaia BH1 proves that chaos can hide in plain sight. It proves that you can be orbiting a monster and not even know it. As we stare into the empty space where Gaia BH1 resides, we are looking at the future of astronomy. For decades, we have been like children, searching for seashells on the beach, picking up only the shiny, bright ones that catch our eye. We mapped the pulsars, the quasars, the bright nebulae, but the ocean is deep, and the things that do not shine are far more numerous than the things that do. "3,000 light-years away, a star is being slowly eaten alive. It has no voice, no way to cry out, but if you could see it up close, you would witness something profoundly disturbing. A quiet orange star is being stretched and pulled apart by something it cannot see and cannot resist. Streams of glowing gas spiral away from its surface like blood drawn from a wound, circling faster and faster into a dark absence at the center. This is V616 Monocerotis, one of the closest known feeding black holes to Earth. You might wonder we have other black holes near companion stars like Gaia BH1, where a star orbits peacefully with no violence at all. So what makes this one different? The answer is distance. In Gaia BH1, the star orbits safely about 1 astronomical unit away too far for the black hole to reach. Here, in V616, the star orbits so close that 1 full revolution takes just 7.75 hours. At that range, the black hole does not just pull, it feeds. To understand this difference is to understand everything about what makes V616 Monocerotis so terrifying. Gaia BH1 is a predator, sitting quietly beside untouched prey. The companion star there is a sun-like object orbiting at a comfortable distance, roughly the same gap that separates our Earth from the Sun. There is no accretion disk, no X-ray emission, no detectable sign of feeding whatsoever. The star simply orbits intact and undisturbed, as though it does not even know what it is dancing with. 16 Monocerotis is the opposite of that silence. Here, the orbital separation is so small, the gravitational grip so suffocating that the black hole physically deforms the shape of its companion. Same ingredients, a black hole and a star, but the distance between them changes everything. The system sits embedded within the disk of our Milky Way, closer to us than most people would find comfortable. At roughly 3,000 light-years, V616 Monocerotis is not some abstract phenomenon at the edge of the observable universe. It is a neighbor. The black hole at its heart carries the mass of 6 to 7 suns, compressed into a region of space-time so warped that nothing not light, not information, can escape its boundary. Orbiting this invisible predator is a K-type orange dwarf, a modest body with roughly half the mass of our Sun. The two circle each other in an orbit so tight that a single revolution takes less time than a human workday. If you blinked through an entire orbit, you would miss one complete cycle of a star being devoured. and with every single orbit, that star loses a little more of itself, quietly, relentlessly, without any possibility of rescue. If you could stand on a hypothetical world nearby and watch this system through a telescope, you would see something deceptively calm. A small orange star, slightly distorted, glowing softly against the black velvet of space. You might not even notice anything wrong at first, but look closer. The star is not round. It is stretched into a teardrop, its outer atmosphere pulled toward a point in the sky where nothing is visible, but where everything is being drawn. This is the signature of Roche-Lobe overflow, a process in which the black hole's gravity reaches across the gap and peels away the star's outer layers, one thin stream at a time. The star is not exploding. It is not being crushed. It is being undressed slowly and mercilessly by gravity itself. From Earth, we see only a faint flicker. To us, it looks peaceful. But the reality is anything but. And this is where the horror becomes personal. The companion star did not choose this fate. Billions of years ago, it was likely part of an ordinary binary system, two stars born from the same cloud of gas and dust, orbiting each other in peace. But its partner was massive, perhaps 15 to 20 times the mass of our Sun, and massive stars live fast and die violently. When that larger star exhausted its nuclear fuel, it collapsed catastrophically, either through a supernova or perhaps through a silent implosion known as a failed supernova. What remained was a black hole. The surviving companion found itself suddenly orbiting not a sibling, but a grave. It had no way to leave. The gravitational bond held firm. The dance continued, but the music had changed forever. This is not a distant catastrophe. It is a glimpse of how stars die when gravity decides to be patient. The disk glows furiously across the electromagnetic spectrum, from radio waves to visible light to blistering X-ray radiation. If you were standing anywhere within a few light years of this system, the radiation pouring from that disk would be lethal beyond any biological tolerance. The black hole does not just consume quietly, it turns its meal into a beacon of destruction visible across the galaxy. For most of its existence, V616 Monocerotis wears a mask of calm. The system is classified as a soft X-ray transient, which means it spends the majority of its time in a quiescent state. The accretion disk glows faintly, material trickles inward at a modest rate, and the system barely registers on our instruments. You could be forgiven for thinking the danger had passed, but deep within, the disk pressure is building. Gas accumulates, temperatures rise unevenly, and thermal instabilities begin to ripple through the structure like fault lines before an earthquake. The system is not resting, it is loading. And when the threshold is finally crossed, what follows is something astronomers have witnessed firsthand and will never forget. The calm is not peace. It is the breath before the scream. Then, without warning, the dam breaks. Material piling up in the outer disk reaches a critical threshold, triggering a cascading avalanche of gas plunging toward the event horizon. The X-ray luminosity spikes by orders of magnitude. The system erupts. In 1975, astronomers witnessed exactly this when the Ariel 5 satellite detected a massive X-ray transient from V616 Monocerotis, an event so bright it became one of the landmark discoveries in high-energy astrophysics. In optical wavelengths, the source brightened by several magnitudes, briefly visible even through modest telescopes. The outburst lasted months before the system slowly dimmed, settling back into deceptive quiet. This was not a one-time event. It was simply one breath in a cycle that has repeated for millions of years. And somewhere inside, that quiet disk pressure is building once again. Imagine watching this from orbit around the doomed companion star. Below you, the star's surface churns and bulges its atmosphere, visibly flowing toward a point in the sky where nothing is visible but where everything is being drawn. Streams of luminous gas arc upward, tracing elegant spirals that accelerate as they approach the unseen center of the disk. The light from the inner accretion region is blinding, flickering with chaotic intensity, and at the very center of it all, there is simply an absence. No surface, no glow, no reflection, just a boundary beyond which the universe stops sharing its secrets. The event horizon. Everything that crosses it is gone, permanently, irreversibly, without negotiation. The star cannot escape. The discovery of V616 Monocerotis was itself a turning point in human understanding. For decades, black holes existed only as mathematical ghosts' predictions, written in the equations of Einstein's general relativity that many physicists suspected might never correspond to real objects. V616 helped change that. By carefully measuring the radial velocity of the companion star, watching it wobble under the invisible pull of its dark partner, astronomers were able to weigh the unseen object. The study of this system has opened windows into the most extreme physics the universe has to offer. By analyzing how X-ray light flickers during outbursts, scientists have probed the geometry of space-time near the event horizon. These observations reveal information about the innermost stable, circular orbit, the last distance at which matter can circle the black hole before plunging irreversibly inward. The measurements have confirmed predictions of general relativity with extraordinary precision. Researchers have even begun to constrain the spin of the black hole, determining how fast space-time itself is being dragged around by the rotating singularity within. From Earth, 3,000 light-years away, using nothing but captured photons, humanity is mapping the shape of the abyss. And what we are finding matches exactly what Einstein predicted over a century ago. But the worst part of this system is not the feeding, it is the future. As mass transfer continues over millions of years, the companion star will shrink. Its hydrogen envelope will be steadily stripped away, leaving behind a progressively smaller, dimmer remnant of what was once a living star. The orbital dynamics will shift as angular momentum is redistributed and lost through gravitational radiation and magnetic braking. Some models predict the orbit will tighten further, intensifying the rate of cannibalism, triggering more frequent and violent outbursts. Others suggest the companion may eventually lose enough mass to detach from its Roche lobe, entering a permanent quiescent state. Either way, the end is the same: a shrunken stellar corpse circling a dark void that consumed everything it once had. The star will not die in a blaze. It will simply fade until nothing remains. During its active phases, V616 Monocerotis does something else that defies comprehension. Not all infalling material crosses the event horizon. Some is seized by powerful magnetic field lines, threading the accretion disk and violently redirected outward as relativistic jets, narrow beams of ionized plasma screaming away from the black hole at speeds approaching that of light. These jets carry staggering amounts of energy into the surrounding interstellar medium. Closer than the distance from our Sun to the nearest star, these jets would obliterate anything in their path. The black hole does not just consume, it broadcasts its violence across the galaxy. A lighthouse powered not by electricity or fusion, but by the destruction of a star that once burned peacefully in the constellation of the Unicorn. The constellation Monocerotis, where this predator resides, lies along the galactic plane between Orion and Canis Major, a region rich with star-forming nebulae, open clusters, and young stellar populations. The presence of a confirmed feeding black hole here is a sobering reminder that such objects are not confined to the distant or exotic. Current estimates suggest the Milky Way harbors between 100 million and 1 billion stellar mass black holes, the vast majority undetected because they produce no radiation. They drift in silence, invisible and patient. Some orbit companions that remain untouched, like Gaia BH1. Others, like V616, have already begun their meal, and countless more float alone through the void, waiting for an encounter that may never come. V616, Monocerotis, is a system defined by patience and inevitability. The black hole does not rage. It does not hurry. It simply pulls orbit after orbit, stream after stream, taking what gravity entitles it to take. The companion star grows weaker with each revolution, its light dimming by imperceptible degrees across millennia. And somewhere out there, in the endless black, between the stars, the next cannibal is already circling its prey. The only question is whether we will find it before it finishes its meal. Our journey into the abyss has only just begun.
If Gaia BH1 cracked open the door, then Gaia BH2 blew it completely off its hinges. Just 1 year after astronomers were still absorbing the shock of finding a silent black hole in Ophiuchus, the same Gaia spacecraft returned with a second discovery, this time from the constellation Centaurus, roughly 3,800 light-years away. Centaurus is one of the most studied stretches of southern sky in astronomy. It contains Alpha Centauri, the closest star system to our Sun, and generations of researchers had swept it with their best instruments and moved on, confident they understood what was there. They were wrong. Hiding in plain sight, camouflaged behind the glare of a companion star, was a black hole weighing nearly 9 times the mass of our Sun, perfectly still, utterly dark, and invisible to every telescope that had ever pointed in its direction. What immediately separates Gaia BH2 from its sibling in Ophiuchus is not just its greater distance or its heavier mass. It is the nature of the star it keeps company with. The companion beside Gaia BH1 is a calm, sun-like star living comfortably in the most stable phase of its life, orbiting the black hole at a safe distance, undisturbed and unthreatened, as though it does not even notice what it dances with. Gaia BH2 is a far more unsettling arrangement. Its companion is a red giant, a star that has already exhausted most of its hydrogen fuel. Hole's gravity reaches across the gap, peels away the outermost layers of the giant, and draws streams of superheated gas into a glowing spiral that blazes in X-ray light visible across the galaxy. That is precisely how most of our known black holes were first discovered. They were caught in the act of feeding. Gaia BH2 carries 9 solar masses of gravitational pull and has a structurally fragile, swollen, red giant sitting right beside it. By every proof, we know by every piece of physics that governs how these systems evolve, it should be one of the most energetic and detectable feeding systems in our corner of the galaxy. Instead, the red giant sits entirely undisturbed, its atmosphere perfectly intact. The answer to why lies in distance. The black hole and the red giant are not close. They are separated by a gap that is wide even by solar system standards. And because of that gap, the black hole's gravitational pull does not reach the giant's outer atmosphere with enough force to strip material free. Think of it like standing near the edge of a cliff. You feel the pull, you lean slightly toward it, but you never quite lose your footing. The threshold for mass transfer is never crossed. The giant holds its layers. The black hole receives nothing. And so the two objects drift around each other in a slow, wide arc that has continued unchanged for millions upon millions of years without a single gram of material moving between them. This is a system that looks, from the outside, like nothing is happening at all. A red giant slowly aging, glowing softly in the light of distant stars. A dark point in space, orbiting quietly alongside it. Invisible to every form of light we know. No fireworks, no radiation, no signal of any kind. And yet here is what makes that silence so striking. The wider the orbit, the more extraordinary the survival story behind it. In almost every black hole binary system we have ever found, the orbits are tight, sometimes uncomfortably tight, the two objects whipping around each other in hours rather than years. A wide, stable orbit like this one does not form by accident or persist without reason. It survives only if the event that created the black hole caused no significant disruption to the system's geometry. And the event that creates a 9 solar mass black hole is almost never insignificant. That is the real puzzle hiding inside this system's quietness, not the silence itself, but the fact that everything around it is still in one piece. Wide orbits in black hole binary systems are not the norm. They are genuinely unusual, and their rarity is not a coincidence. It is a direct reflection of how catastrophically violent the birth of a black hole tends to be. Most known feeding black holes inhabit very tight binaries, systems shaped by long histories of mass exchange and gradual orbital decay. For a wide, stable orbit like the one in Gaia BH1 to exist today, the event that created the black hole must have left the surrounding system almost completely untouched. But creating a 9 solar mass black hole requires the death of a star that was likely 25 to 40 times the mass of our Sun, a massive, short-lived giant that would have ended its life in a supernova, one of the most energetic explosions the universe produces. Shock waves from supernovae travel at tens of thousands of kilometers per second and carry enough energy to reshape the interstellar medium for thousands of light years in every direction. If the red giant's ancestor was in orbit when that explosion happened, the shock wave should have battered it with brutal force, stripping its outer atmosphere, drastically altering its orbit, or simply breaking the gravitational bond between the two objects entirely, sending the companion flying into the galaxy forever. None of that happened here. The companion stayed. The orbit remained wide and stable, as though the birth of the black hole was no more disruptive than a change in the weather. Everything that should have been shattered by the arrival of this black hole somehow endured it without a scratch, without a wobble, without any evidence that the most violent transition in stellar physics had occurred just next door. And that is where the science becomes deeply uncomfortable, because our best models say it simply should not have been possible. Here is where the mystery stops being a puzzle and starts being a crisis for conventional thinking. Stars between 25 and 40 solar masses are not gentle in death. They live fast, burning through their fuel in just a few million years, and when the collapse comes, it happens in less than a second. The core implodes with a violence that defies comprehension. In nearly every case we have ever modeled or directly observed, what follows is a shock wave, a supernova that briefly radiates more energy than every other star in the Milky Way combined. If the red giant we see today was orbiting that massive blue star when it exploded, the consequences should have been catastrophic. The shock wave should have slammed into the red giant's ancestor with enough raw force to strip layers of atmosphere from its surface and throw it violently onto a completely different orbital path. The sudden loss of mass from the dying star alone would have changed the gravitational balance of the system so abruptly that the companion had no choice but to be flung outward, breaking free from the binary entirely. We have seen this exact outcome in other systems, pairs of stars torn apart by the violence of one partner's death, companions scattered into the galaxy at high velocity, binaries that simply could not survive the shock. The math is solid and well tested across decades of observation and confirmed across multiple binary systems. Yet the red giant in Gaia BH2 is still orbiting, still intact, circling a black hole that, by every conventional model, should have announced its birth with a visible catastrophe powerful enough to leave a permanent mark on the surrounding space. As if the black hole simply appeared one quiet day without any sound at all, and the companion just kept going. One explanation has been gaining serious traction among researchers. This black hole may never have exploded. There is a growing body of work around a phenomenon called direct collapse, or a failed supernova, where the internal conditions of a dying massive star prevent any outward shockwave from forming. Instead of detonating, the star falls entirely inward, all at once, all of it. The outer layers find no explosion to ride outward, and so they collapse too. The star does not flash. It does not scream across the electromagnetic spectrum. It simply vanishes. One moment a massive blue giant burns in the sky. The next moment there is nothing, just a black hole sitting in the precise space the star used to occupy. No blast wave, no shock front, no sudden redistribution of mass that the companion could feel as anything out of the ordinary. The gravitational pull on the companion barely even shifts, and so the orbit that existed before the collapse continues forward as if nothing in the universe has changed. Now circling a dark absence instead of a blazing star, the companion pulled along by the same quiet force it has known for its entire life. Astronomers have been searching for direct collapse events in distant galaxies for years, watching populations of massive stars and looking for cases where a giant simply disappears without producing a detectable explosion. Several credible candidates have been identified. Gaia BH2 may be something still rarer. Not just a failed supernova candidate, but its preserved and observable aftermath, the black hole still quietly orbiting the companion it never had reason to destroy, the two of them circling each other in a system that carries no evidence of the catastrophe that never came. Think about what that means for a moment. If a star 30 times the mass of the Sun collapsed silently within 500 light-years of Earth right now, we would not see it, hear it, or detect it in any way. No flash, no shockwave, no expanding shell of gas to find centuries later. The black hole would simply appear, drift into the dark between the stars, and wait. Consider the scale of that invisibility. If Gaia BH2 existed where our Sun is, its gravitational influence alone, 9 solar masses pulling from the center of our solar system, would have long ago torn the planets from their orbits. Earth would not exist. The asteroid belt, Jupiter, everything we consider our neighborhood would have been scattered or consumed. Yet from 3,800 light-years away, it looks like nothing. That is the nature of what we are dealing with. Astronomers already estimate that the Milky Way harbors between 100 million and 1 billion stellar mass black holes, the overwhelming majority undetected because they radiate nothing. But that estimate rests on models that assume most massive stars die through supernovae, deaths that leave behind expanding remnants we can eventually catalogue and count. If even a modest fraction of those stars instead collapse silently, then the estimate is not just incomplete, it is built on a foundation that never accounted for the quietest deaths. Every silent collapse is a black hole that entered the galaxy without leaving a forwarding address, one that joined the dark and left no record of its arrival. The galaxy has been accumulating these invisible masses since its earliest ages, and Gaia BH2 is the first physical evidence the process has been happening all along, quietly and persistently.
The black holes we have visited so far share one defining quality. They hid. They were found by accident, betrayed by gravitational whispers, detected only because instruments precise enough to track 1 billion stars eventually caught the subtle wobble of a companion moving in ways it should not have been moving. Gaia found them, not because they announced themselves, but because extraordinary patience and precision eventually revealed what the eye could never see. But now, we leave that era entirely. We travel 7,200 light-years into the Milky Way, into the constellation Cygnus, and we arrive at something fundamentally different, something that did not hide, not even slightly. It did not need to be hunted by orbital mathematics or satellite surveys running for years. From the moment we built instruments capable of hearing it, it was already there, blazing in X-ray light, so intense and so concentrated that it was among the very first things those instruments ever found. Cygnus X1, a 21 solar mass black hole, actively tearing material from one of the most powerful stars in our galaxy, converting stolen mass into radiation with an efficiency no nuclear process on Earth can come close to matching. It is the first black hole humanity ever confirmed as real. Confirmed, with a measured mass, a known address in the sky, and a companion star that anyone with a sufficiently powerful telescope could find and track. And the story of how that confirmation was finally reached, the long decade of uncertainty, the wager it forced between two of the most brilliant physicists alive, and what it cost one of them to concede, tells us as much about scientific belief as it does about the physics of collapsed stars.
In the early 1960s, the X-ray sky was a complete blank. X-rays from space cannot penetrate Earth's atmosphere, which means every ground-based telescope ever built is entirely blind to them. Seeing X-ray light from space required going above the atmosphere, and in 1962, that meant strapping detectors to a suborbital rocket, pointing it at the sky for just a few minutes, and trusting the instruments long enough to get data back before they crashed into the ocean. On June 18th of that year, a team led by physicist Riccardo Giacconi did exactly that. The rocket carried Geiger counters above the atmosphere for just under 6 minutes. 6 minutes. And what came back changed the field permanently. The detectors had found real, powerful, concentrated X-ray sources, with no obvious explanation. Objects that had been there all along, invisible to everything humanity had ever built, until that moment. One source, coming from the direction of Cygnus, was so bright it stood out immediately. It was catalogued as Cygnus X1. In 1962, black holes were still theoretical. Mathematical solutions to Einstein's equations that many serious physicists assumed might never correspond to anything real. A black hole was one possible explanation, then quietly set aside for lack of proof. What the source truly was would take another decade of increasingly precise measurements to establish. And establishing it would require more than just better data. It would require a personal wager between two of the most influential physicists of the 20th century. A bet one of them spent 16 years hoping he would win. Staked not on money, but on something far more personal. The kind of intellectual insurance only the most honest minds allow themselves.
The answer came not from studying the X-ray source itself, but from the star beside it. Once astronomers pinned down a precise position for the signal, they turned their optical telescopes to the same patch of sky and found HDE 226868, a blue supergiant, carrying roughly 40 times the mass of our Sun, one of the most intrinsically luminous types of stars anywhere in the universe. A star like that
does not sit next to a screaming X-ray source by coincidence. When astronomers measured the motion of HDE 226868 by watching the Doppler shift of its light, its spectral lines shifting back and forth as the star moved toward and away from us in its orbit, they confirmed it was circling something invisible. One full revolution every 5.6 days. Fast, tight, locked. The mass calculation that followed was the moment everything became uncomfortable. The unseen companion had to weigh at least 8 solar masses just to produce the orbital motion observed. 8 solar masses is well above the maximum any neutron star can hold before collapsing further under its own weight. The only known object that carries that much mass and remains perfectly dark, no surface, no radiation, no light of any kind, is a black hole. For the first time in history, the data was not merely suggesting a black hole as a possibility. It was demanding one. There was no honest alternative, no exotic object that could account for the mass, no neutron star anywhere near that weight. The only response was to accept what the numbers had always been saying, that something real, something beyond any previously known category of object, had been sitting 7,000 light-years away in Cygnus, feeding continuously, long before any human ever wondered what a black hole was. Even then, not everyone did. In 1974, Stephen Hawking, the physicist who had spent his career building the theoretical framework for black holes, placed a personal bet against Cygnus X1 being one. His colleague, Kip Thorne, took the other side. The terms were simple: a magazine subscription. But the reasoning was not trivial at all. Hawking called it an insurance policy. If black holes turned out not to be real, then the theoretical work of a lifetime would be left without foundation. And at least, he would have won the bet. It was a hedge. It was Hawking, the foremost living expert on black holes, quietly admitting he could not be entirely certain the universe obeyed the equations he had spent his life developing. That admission is worth sitting with for a moment, because it cuts to the heart of how science actually works. The man who understood black holes better than anyone on Earth was not willing to stake his certainty on one actually existing. There is nothing weak in that. It is what intellectual honesty looks like at the highest level. 16 years passed. Instruments improved. Measurements of HDE 226868's orbit were refined again and again. The invisible companion's mass climbed steadily, past 10 solar masses, past 15, settling finally at 21. No neutron star, no exotic alternative, no escape from the conclusion the data had been building toward since 1962. In 1990, Hawking signed the concession. The universe had been right all along. And a bet placed against the existence of something that had been feeding, blazing, and carving its signature into the surrounding gas for millions of years before any human civilization existed, was finally, formally, and quietly closed. The black hole did not notice. It kept going, exactly as it always had. Physically, Cygnus X1 is a system of extreme contrasts, compressed into a brutally small space. 21 solar masses of collapsed spacetime, squeezed into a region roughly 60 kilometers across, in a tight orbit, with a blue supergiant star so vast its surface would reach past the orbit of Mars if it replaced our Sun. The two objects circle each other every 5.6 days, at a separation smaller than the distance between the Sun and Mercury. At that range, the star's stellar wind, the continuous outpouring of gas that stars of this mass exhale at millions of kilometers per hour, pours directly over the black hole. The captured gas does not fall cleanly inward. It has angular momentum. It spirals. It builds a rotating disk of superheated plasma surrounding the black hole. And at the disk's innermost edge, temperatures reach tens of millions of Kelvin. Hotter than the core of any star. Hotter than any nuclear detonation. Hot enough to radiate powerfully in the X-ray band across thousands of light years. That is what blazes from this system. A disk that has been announcing itself across thousands of light years since long before we had instruments to hear it. Not the black hole itself, which, like every black hole, produces no light of any kind from its own structure, but the final luminous scream of gas at the last boundary it will ever cross. The event horizon itself is invisible. It always will be. What we see is everything just outside it. The gas accelerating toward a boundary, beyond which the laws of physics, as we understand them, stop providing answers. Nothing that has ever entered a black hole's event horizon has returned. Nothing that enters one ever will. The boundary is absolute, and it has been absolute since long before the first human looked at the sky. Not all of that gas crosses the horizon. A fraction is seized by powerful magnetic fields threading the inner disk and hurled outward in the opposite direction. Narrow, focused beams of plasma, accelerated to speeds approaching that of light. These are relativistic jets, and they are the most counterintuitive feature black hole systems produce. We picture black holes as pure consumers, things that only take. But through a process called the Blandford-Zanajek mechanism, the spinning black hole and its surrounding magnetic field work together as an engine, extracting rotational energy from the black hole itself and broadcasting it outward with more energy per unit mass than any other process the universe generates. This is not a minor detail. The jet from Cygnus X1 has been driving into the surrounding interstellar medium for millions of years, inflating, expanding cavities in nearby gas clouds, structures so large they dwarf anything stellar winds alone could create. A black hole does not simply consume and fall silent. Something else happens to the material that does not cross the horizon. It gets redirected, accelerated,
launched back into the galaxy with more energy per unit mass than virtually any other process the universe produces. It leaves marks, permanent ones, the kind that outlast any individual outburst by millions of years. Cygnus X1 was one of the first systems where these mechanisms were studied in enough detail to understand what was happening. And the models built here became the foundation of everything we now know about how black holes shape the space around them. The jet is not a side effect of the feeding. It is a fundamental output, carrying as much physical significance as the disk itself. We did not know that until we had this system to study.
The confirmation of Cygnus X1 was not just a scientific result. It was a threshold that could not be uncrossed. Before it, black holes existed only in equations, uncomfortable predictions that many physicists quietly hoped a more complete theory might eventually dissolve. After it, there was a black hole at a specific address. We could point at the sky and say, "There, that one." We had measured its mass. We had watched it feed. 60 years after Einstein wrote down general relativity and the mathematics first implied these objects could exist, the universe had delivered its answer. The mathematics was right. Gravity can compress matter past every counterbalancing force. There are real places in space where the escape velocity exceeds the speed of light, where the boundary between existence and non-existence is not an idea, but a physical surface. What followed was an entirely new field. Dozens of X-ray satellites, systematic black hole surveys, a new generation of instruments built specifically to hear what had always been there. Cygnus X1 did not just prove that black holes were real. It gave us the method to find all the others. The mass function method, weighing an unseen object through its gravitational grip on a visible companion, was refined here. And it has been applied to every binary black hole confirmed since. Every system in this journey, every black hole we have confirmed, or will confirm, traces its lineage back to a single moment. A Geiger counter, rising above Earth's atmosphere for 6 minutes on a June morning in 1962. 6 minutes that changed what humanity knew about the universe. Cygnus X1 is still active, right now. Still feeding, still blazing, still pulling its companion through that 5.6-day orbit with a grip that has not loosened in millions of years. The star is losing mass with every revolution. Its future already written. As it ages and expands, the rate of transfer will grow. The disk will intensify. The jets will reach further into the surrounding gas. And eventually, the star will exhaust its fuel and die in the gravitational presence of an object that has already survived its own death. What happens next is still uncertain. What happens when a massive star collapses beside an existing black hole is a question astrophysics has not fully answered. But we leave this system having crossed a line. The journey so far has moved from silence to sound, from black holes so still and so dark that a billion-star survey was needed to accidentally find them, to a system that was blazing before our instruments existed to hear it. That contrast is not just scientific. It is a reminder of how much was always there, waiting, long before we had the means to find it. We are not discovering the cosmos, we are catching up to it. The black holes were always there, feeding, burning, reshaping the space around them, across timescales that make the entirety of human civilization invisible by comparison. Every object in this journey was doing exactly what it does, long before the first telescope was built. We simply, finally became precise enough to notice. And what is waiting, further out, will make everything we have seen so far feel, in the most honest and humbling terms, like a quiet prologue. Cygnus X1 gave us a picture of what an active black hole looks like when it has found its rhythm. Steady, relentless. A machine running on stolen stellar wind, blazing in X-rays with the consistency of something that sees no reason to change. We left that system with a model that felt complete. Active black holes announce themselves, and they keep announcing themselves. It was a reasonable conclusion. It was also only half the picture. 600 light-years deeper into the same constellation of Cygnus, buried in a system so faint our instruments barely registered it, is a black hole that spent 26 years appearing to do almost nothing, and then, without a single moment of warning, became one of the brightest X-ray sources in the entire sky. Not by intensifying slowly, not by giving observatories time to repoint, by crossing a threshold no telescope had caught, and releasing in a matter of hours everything it had held for more than 2 decades. This is V404 CYGNI, and the lesson it carries is not the same lesson as the one before. Cygnus X1 showed us what a black hole looks like in equilibrium. V404 CYGNI shows us what happens when that equilibrium breaks. Silence and catastrophe are not opposites here. They are chapters, the same story told across different timescales. And it leaves us looking differently at every quiet system we have ever cataloged and moved past. Not with fear, with something closer to recognition. The understanding that calm in this part of the universe is a temporary condition rather than a permanent state. That the thing orbiting unremarkably in a catalog somewhere may be one threshold away from becoming the loudest object in the local sky. V404 CYGNI does not change what a black hole is. It changes what we understand the word patient to mean, when applied to something with 9 solar masses of gravity at its center. V404 CYGNI sits 7,800 light-years from Earth, anchored around a black hole of roughly 9 solar masses. Its companion is a modest orange dwarf, half the mass of our Sun, circling the black hole every 6.5 days at a distance close enough for gravity to reach continuously into the star's outer layers. Material flows. the disk forms. But V404 CYGNI does not process that stolen gas the way Cygnus X1 does. It stores it. Month after month, year after year, the outer disk accumulates material while the system presents a nearly silent face to our instruments. An X-ray signature so faint it sits at the edge of what detectors register as meaningful. A survey telescope would log it as a dim, unremarkable binary and move on. And that apparent calm is not accidental. It is structural. The disk cannot release what it has accumulated until a specific internal threshold is crossed. A threshold with no fixed schedule, no warning signal, no external trigger. The reservoir fills in the dark. It fills without announcement. And when it finally reaches the condition that changes the physics of how energy moves through the plasma, the cascade begins. Within hours, not days, everything that was waiting becomes everything that is happening. A system that looked like almost nothing transforms into one of the most energetic objects in the local galaxy. And the only way to have predicted it was to have known where it was in a cycle no model can yet time precisely. That limitation is not a failure of the models. It is a property of the system itself. The instability threshold is sensitive to temperature gradients, viscosity profiles, and asymmetries in how gas settles into the disk. Variables too fine-grained for any current instrument to measure directly. Timing cannot be predicted. Initial conditions cannot be fully known. The disk fills in the dark. The physics behind this transformation has a name: disk instability. When accumulated gas in the outer disk crosses a critical ionization threshold, the way energy propagates through the plasma changes abruptly. A wave of altered viscosity moves inward. Material that had been sitting in the outer regions for years begins flooding toward the center. And the inner disk, suddenly receiving that surge, heats to tens of millions of Kelvin in a matter of hours. Luminosity climbs by a factor of thousands. Not gradually, not over weeks, in hours. Brightness changes that would take an ordinary star millions of years to produce happen here in a single human shift. Within that window, V404 CYGNI goes from barely detectable to one of the most luminous X-ray sources in the galaxy. Previous outbursts, including the major event recorded in 1989, were partially missed because of this speed. By the time a detection was confirmed, a decision made, and a telescope repointed, the source had moved through several distinct luminosity states. The instability outruns the infrastructure built to observe it. The 2015 outburst changed that. Swift, a satellite designed specifically to eliminate that delay, caught the event early enough to watch the outburst still building toward its peak. What it found was a system already operating far outside anything considered routine. Flickering in brightness on timescales of minutes, shifting between luminosity states faster than the previous generation of instruments could have logged. Behaving in ways the 1989 outburst had hinted at, but never confirmed. Because the tools of 1989 had not been built for something this fast, this bright, or this chaotic. Swift had been, for the first time, every stage of a major outburst from this system was caught in real time. From the first hard X-ray surge to the slow fade of the weeks that followed. On June 15, 2015, at the edge of the constellation Cygnus, V404 CYGNI announced itself. Swift detected the hard X-ray burst and automatically alerted observatories worldwide. Within hours,
every major space telescope in operation had turned toward it. What they found was the first major outburst from this system in 26 years. The disk had been filling since the Berlin Wall fell, since the first website went online, since Hubble was launched with a flawed mirror and repaired by human hands in orbit. All of that time accumulating. All of that time waiting. And now it was releasing. The outburst lasted several weeks and was observed simultaneously across every wavelength: radio, infrared, optical, X-ray, gamma ray. Telescopes on the ground and in orbit took turns watching as the system moved through states that changed faster than any single facility could track alone. The data that came back generated more scientific papers in a shorter window than any comparable black hole event in the preceding decade. Not simply because it was bright, though it was extraordinary in luminosity, but because it was simultaneously doing things that had only ever existed as theoretical possibilities. Behaviors that appeared in models under specific conditions, but had never been confirmed in any real system. All of them unfolding at once, across every frequency, in full view of every instrument humanity had managed to point at that region of sky, in that particular window of time. The 2015 outburst was not just an event. It was, in the language of high-energy astrophysics, a once-in-a-generation window. And the community responded with every instrument it had available, on the ground and in orbit, pointed at a single point in Cygnus.
What those instruments recorded was not organized violence. It was closer to a system at war with itself. The X-ray brightness did not climb to a peak and hold. It flickered. It spiked by a factor of 10, then dropped, then spiked again. The disk was not feeding the black hole in a steady stream. It was dumping material in irregular avalanches, overloading the inner disk, briefly choking the infall, then flooding again with the next surge. And at the peak of those surges, something remarkable happened. The system became so luminous that its own radiation began pushing material away from the disk, outgoing energy strong enough to counteract the gravity drawing the next layer of gas inward. The black hole had become, in the most literal physical sense, too violent to eat efficiently. This is the Eddington limit made real, not as a number in a textbook, but as a visible contest between radiation and gravity, playing out across a disk of plasma 7,800 light-years away. Each time the outgoing pressure overcame infall, the surge collapsed. Then material flooded again. Then the limit was hit again. A cycle within a cycle. The large outburst containing dozens of smaller ones. Each spike in the X-ray light curve lasting minutes before collapsing. The system oscillating between gluttony and choking, with a rhythm no model had predicted at this frequency or intensity. Watching the light curve from V404 CYGNI during those peak weeks was an exercise in sustained disorientation. Each spike peaking higher or collapsing faster, the pattern defying any expectation that the next data point would resemble the last. Researchers who had spent careers studying X-ray transients described it as unlike anything they had encountered before. Not because outbursts were unknown, but because none had been captured at this resolution, at this complexity, in real time. Then came the jets, and they were unlike anything ever recorded from a stellar mass black hole. Cygnus X1 launches jets that are narrow, stable, and persistent, pointing in the same direction for millions of years, carving the same channel through the surrounding gas. V404 CYGNI's jets were rotating. Radio images taken just days apart showed plasma emerging, not from a fixed axis, but sweeping, shifting direction by significant angles between observations. The jet was not a beam. It was a lighthouse. The inner accretion disk had been warped by the black hole's spin into a configuration that was itself precessing, a process called frame dragging in general relativity, where the rotation of a massive object distorts space-time and drags nearby matter into misaligned orbital planes. Those tilted inner regions were launching plasma in directions that changed as the disk precessed around the spin axis, and each direction was recorded in the surrounding gas, like a frame of film. Taken together, the sequence of radio images described a spray of expanding plasma knots, fanning outward across multiple directions. Not the clean opposing jets of a stable system, but a chaotic arc of ejecta encoding the black hole's rotation history in the interstellar medium around it. V404 CYGNI had, without being asked, performed a live experiment in strong field general relativity, in a regime where space-time curvature near the event horizon is large enough to measurably deflect the orientation of an infalling disk. And the results matched what theory had predicted, for a spinning black hole embedded in a warped disk, precessing under frame dragging. No ground-based laboratory can replicate those field strengths. V404 CYGNI did it naturally, and the rotating jets it produced in June 2015 confirmed predictions that had been waiting decades for a system willing to demonstrate them.
There is no universal black hole, not as a caveat buried in a paper, as an observational fact. The same object, 9 solar masses of collapsed spacetime, orbiting the same companion at the same distance on the same 6.5-day cycle, spent 26 years looking like almost nothing, and several weeks being one of the most energetic sources in the galaxy. Both were the same black hole. Neither description captures it completely, without the other. What separated them was not structure, not mass, not companion type. It was a single quantity, the amount of gas in the outer disk, and the precise moment that quantity crossed a threshold. The patient version and the violent version are not different objects. They are different phases. And this matters beyond V404 CYGNI, because every quiet, unremarkable, low luminosity binary in our catalogs carries the same possibility. Not every one of them is accumulating toward an outburst, but the ones that are look identical to the ones that are not. From this distance, with these instruments, in this moment of observation. And we have no reliable current method to determine which ones, only the knowledge that the process, where it is occurring, is continuous.